Welcome back everyone, it's another day, and today we're going to be covering a brand new concept, a whole new way to look at numbers. These number formats are called binary and hexadecimal number formats. A lot of us are used to seeing numbers like 1234, 12, 3 even. And these numbers consist of digits from 0 to 9 and any number of them put together. If we look at 1, 2, 3, 4, and I add any number of zeros in front of it, we still consider this number to be a valid number, and it's just 1234. Now, if we were to break down each of these numbers a little bit more and look at how many digits they have, it might seem a little bit weird at first, but bear with me. We can view these numbers almost as a sum of some things. So we can think of it as 4 multiplied by 1 plus 3 multiplied by 10 plus 2 multiplied by 100 plus 1 multiplied by 1000. And if we were to look at that a little bit closer, we'd notice that this is 4 multiplied by 10 to the power of 0 plus 3 multiplied by 10 to the power of 1 plus 2 multiplied by 10 to the power of 2, 1 multiplied by 10 to the power of 3. Now, I did not list out the zeros in positions 4, 5, and 6 of the number, because if I were to multiply anything by 0, I'm just going to get the number 0. Now, one really interesting thing to note over here is that the numbers I've just underlined correspond exactly with what place that number is in, or what position in that number that digit is in. And if we look at the number 12, we can represent it almost in the exact same way by saying this is 2 multiplied by 10 to the power 0 plus 1 multiplied by 10 to the power 1. And similarly, we can do 3 times 10 to the power 0 gives us 3. Now, what's really nice about this numbering system is that we can look at all of these and we're always multiplying by some random digit, 0 through 9, multiplied by 10 raised to the power of whatever position that digit is at. So why is it 10? That's because we're using the base 10 numbering system. When we use the base 10 or the decimal numbering system, we are going to multiply the digit by 10 raised to the power that's based on the position of the digit. Now, when I bring up the binary numbering system, what do you think that stands for? That's right, binary stands for a 2-digit numbering system. So the valid numbers that are available to us to make numbers, instead of 0 all the way through 9, are only just 0 through 1. So as long as we put any number of zeros and ones together, just like we did with these numbers above, where we put any number of 0 through 9 together to make a decimal number or a base 10 number, I can put any number of 0 through 1 together to make a binary number. So let's just start listing out some numbers. Let's say 0, 0, 1, 1, 1, 0, 1. Now we have made a binary number. But this could also be a decimal number. So to be a little bit more particular, to really identify this as a binary number, we'll start it with a 0b. So when a number starts with 0b, we can clearly read it to be a binary number. Now let's read the things underneath. Let's label these digits. So this binary number is composed of 7 digits. And if I wanted to compute the value of this binary number in the numbering system that you and I are used to, or the decimal or base 10 numbering system, we can just go ahead and do what we did earlier, where we took every single digit, 1. So the 0th digit is 1, and remember, our base is 2 because it's a binary numbering system. 1 multiplied by 2 to the power 0, plus 0 multiplied by 2 to the power 1, plus 1 multiplied by 2 to the power 2, plus 1 multiplied by 2 to the power 3, plus 1 multiplied by 2 to the power 4, plus 0 multiplied by 2 to the power 5, plus 0 multiplied by 2 to the power 6. Now, one really convenient thing about the binary numbering system, because it's just composed of ones and zeros, is I can quickly simplify this to just be 2 to the power 0, plus 2 to the power 2, plus 2 to the power 3, plus 2 to the power 4. And I can do that because all the zeros are just going to cancel out and just stay as 0, and all the ones are just going to give me the base raised to the exponent power. And if I were to simplify this, this would be 1 plus 4 plus 8 plus 16. And the sum of this is going to be 29. So now I just found out that binary 001101 is equal to decimal 29. Equivalently, I could have just written this to be 0b11101. Because remember, just like in decimal numbers, I can have any number of zeros in front of the leading digit, or in this case, the leading one, and those zeros won't matter at all to the final value of the number. Binary 11101 is decimal 29. So did you get how to convert binary to decimal? Did you see a pattern? Let's try another example, just to be sure. So we'll make a binary number, 0b1111011. Now, this number has the following positions. It has 8 digits, and if we were to list it out, this is equal to 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 4. Notice we skipped 3 because it has a 0 in the third digit. Plus 2 to the power of 5, plus 2 to the power of 6, plus 2 to the power of 7. And then this simplifies down to 1 plus 2 plus 4 plus 16 plus 32 plus 64 plus 128. And if we were to go ahead and simplify this, this would equal to, let's do some scratch work really fast. These two make 20. These two make 150 plus 180. This makes 200. This makes 67. This would end up making 267. So binary 11110111 is decimal 267. If we apply this technique, we'd effectively be able to convert any binary number into any decimal number. That's half the battle. The only thing that's left to do is know how to convert a decimal number into binary. We already know how to convert 267, but what if I asked you, how do we write decimal 100 as a binary number? That'd be really hard. One easy way to do this is we can go ahead and apply our technique of, let's start counting. So let's say we have a decimal number. And on this side, we'll keep track of binary numbers. Let's say we start off with the number 0. So we know decimal 0 is going to be the same as binary 0, which is 0. We also know that decimal 1 is going to be the same as binary 1, which is just 1. So the question becomes, how do we get the next number? Well, in decimal, to get the next number, we're just going to do plus 1, and that is going to give us the number of 2. Well, we can do a similar thing in binary, where if we were to add 1, we should get the next digit. But remember, 2 is not a valid binary digit. So let's try and add in binary to figure out what the next value is going to be. So if we were to add 1 plus 1 in binary, this is very similar to adding 9 plus 1 in decimal. When we add 9 plus 1 in decimal, we find that, hey, we don't have a digit for 10. Instead, we find that this is 0, because it goes to the next available digit, which after 9 just wraps around to 0, and we have a carry of a 1, because that's how many times we've wrapped around so far. So then when we bring the carry down, we go from adding 2 one-digit decimal numbers to having 2-digit decimal number. The same can be done in binary. If we add 1 plus 1, we find that we have no more valid digits left. So instead we're going to wrap around to the very next digit, which right after 1, if we go all the way back around, is a 0. And then how many times did we wrap around? We wrapped around just once. So we have a 1 on top. And since 1 isn't being added to anything else, we're going to bring it back down. So 1, 0 in binary represents the value of 2. Did you get that? If not, let's do a couple more examples to really understand this. Well, what about the next number? How are we going to get that? Well, we're going to add 1 here and then add 1 here. If we add 1 to 2, we'll find that the next digit is 3. And similarly, let's try and figure out exactly what it means to add 1 to binary 1, 0. 1, 0 plus 1 is equal to this. So 0 plus 1 is just 1. And a 1 plus nothing is going to be a 1 as well. So that means 3 must be the value 1 and 1. Let's try one more time. If I were to add plus 1 here and plus 1 here, 3 plus 1 in decimal gives me a 4. A binary 1, 1 plus 1 gives me what? It gives me a 0, because 1 plus 1 is going to wrap around because I have no more digits left, so I'll have a carry of 1. Now I'm doing 1 plus 1 again, which means I have 0 and a carry of 1. And I bring the 1 down. So now 1 plus 1 gives me a value of 1, 0, 0. Are you seeing a pattern here? Well, if I were to go and list out these examples, I can go ahead and continue for a while. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's go ahead and write out what all of these values are. 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. It's pretty neat. I'm basically able to just add 1 by 1 and by 1 until I finally get to the number I wanted. So if I wanted to get to the number 100, in effect, I could really just add 1 100 times starting at 0 until I finally found out what the binary representation of 1 was. Or some of you might say, another way to get to 100 is to add 10 10 times to itself. So I could take 10 and add it to itself 10 times and get the number 100. Let's try that. So 10 is 1010. 1010 plus 1010 gives me 0. 1 plus 1 is 0 with a carry of 1, so 1 goes over here. 1 plus 1 is 0 with a carry of 1. And now this number should be equal to 20. What's really nice about this is I can actually double check my work. If I were to convert this number back to binary, I would get 2 to the power of 4 plus 2 to the power of 2, which is equal to 16 plus 4, which is equal to 20. There you go. So my addition was definitely correct. Now that we kind of have a way of getting to 100, simply by, we could add 10 to itself and get 20, then add 20 to itself to get 40, and add 40 to itself to get 80, and then finally we could add 80 with 20 again to get 100. But that seems very ineffective. Perhaps there's a better way, and there is. One other way to get to 100 is simply by thinking about the number 100. The first thing we need to know is how many digits are going to be in 100. Well, one easy way to check is count up the powers of 2 that we have available. If we were to go ahead and start listing out powers of 2, we would find that 2 to the power 0 is 1, 2 to the power 1 is 2, 4, 8, 16, 32, 64, and 128. Well, we know 128 is bigger than our goal for 100. So the number of digits in binary that the number 100 will have required to represent it is going to be related to how many what power of 2 128 is, because it's the first power of 2 that is bigger than 100. So let's list it out. 3, 4, 5, 6, 7. So our binary number is going to have exactly 7 digits. So let's make room for it. 0b. So now we have a binary number of 7 digits available to us. Let's start filling it out. Well, the first thing we have to ask ourselves is, in our goal of 100, do we have room for 2 to the power of 6? Now, 2 to the power of 6 is 64. So we'll put a 1 here since 100 is more than 64. And then simply we're going to subtract out 64 out of this. 100 minus 64 gives us 36. Well, now we'll go on to the next digit, which is the 5th digit. And we'll ask ourselves, does the number 36 have room for 2 to the power of 5? And 36 is indeed more than 32, so we're going to put a 1 here. And we'll subtract out 32 from this. And that is going to give us 4. And now we're going to go and ask ourselves, does 4 have room for 2 to the power of 4? 2 to the power of 4 is 16, which is more than 4. So we're going to get a 0 over here. Similarly, 2 to the power 3 is 8, which is more than 4, so we're going to get another 0. And then finally, we're going to get to 2 to the power of 2, and 2 to the power of 2 is exactly 4, so it does have room for 2 to the power of 2. So we will set this to be a 1, and then we'll subtract out 4, and we'll get 0. And because we have 0 now, we know that we need no more values or no more powers of 2 to be added. So we're going to fill out everything else with a 0. So the number 100, according to our calculations, should be represented by binary 1100100. Now there's a really easy way to check that. We can just convert from binary back to decimal. And if we remember correctly, our binary number is going to end up equaling 2 to the power 6 plus 2 to the power of 5 plus 2 to the power of 4. And now you might notice that each of these correlates directly with the numbers that we subtracted from 100. So the act of making a number from decimal to binary is really just finding out what powers of 2 added together are going to give you that number. And we always start from the largest power of 2 possible. So in the case of 100 is 64. So we started off with digit 6 being set to a 1. And then once we subtracted that from 100, we went ahead and said, what's the next power of 2 that is bigger than 36? And the next power of 2 is going to be a 32, or 2 to the power of 5. So we set the 5th digit to be true. And then we went all the way down until digit 2 and set a 1 over there because the only value left was a 4 that we needed to subtract out. This is a really neat trick, and as you go ahead and get more practice into this, you'll be able to get faster and faster and faster at this. So now we have learned exactly how to go from binary to decimal and decimal to binary. So let's move on to the next number format, which is a hexadecimal number system. So a decimal numbering system is the base 10 numbering system. A binary numbering system is the base 2 numbering system. The hexadecimal numbering system is the base 16 numbering system. It's actually very similar to the numbering system we've been dealing with, and converting from a hexadecimal to a decimal value is very straightforward. But the only part that's tricky about this is how are we going to have 16 digits? We only have digits 0 through 9. Well, luckily for us, people much smarter than me have already come up with a concept to represent this. The way we count in decimal is we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when we hit 9, we have no more digits left because we've used all 10 of our digits in the base 10 digit system. So we'll go up to 10, or the first 2-digit number. In hexadecimal, we're going to count just like that, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now, because we need more digits to represent all the way up to 16 digits, the next number after 9 is going to be A, and then B, then C, then D, then E, then F, and then we'll go to 1, 0. Now, what's happening here? Well, we have chosen to represent A as equal to 10, and B represents 11, and C represents 12, 13, 14, 15. And can you guess what 10 represents? That's right. 10 is the first 2-digit number, which represents a value of 16. So a decimal number is any number that is comprised of digits 0 through 9. A binary number is any number that's comprised of any digits only 0 through 1. A hexadecimal number is any number that is comprised of digits that are either 0 through 9 or A through F. So if we were to make up a random hexadecimal number, let's just come up with one on the spot. 2AB. So this is a 3-digit hexadecimal number. And if we were to label our positions below, it'd be 0, 1, and 2. And now, how do we convert from a hexadecimal number to a decimal number? Well, it's just like we've been doing before with every other numbering system. We're going to write this as equal to B multiplied by, remember our base is 16, so 16 to the power 0, plus A multiplied by 16 to the power 1, plus 2 multiplied by 16 to the power of 2. So this is equal to, B remember is 11, multiplied by 1, plus A, which is 10, multiplied by 16, plus 2 multiplied by 256. And if we simplify that, that's 11 plus 160 plus 512. And going further, this ends up being 683. Now we can apply the same techniques that we've been applying everywhere else, where we take the digit, multiply by the base, raised to the power of the position the digit is in, to be able to convert from any base into base 10. Well, now the only question that remains is, how do we go from hexadecimal to decimal? Well, that's actually not that hard, but it requires you to memorize a lot of powers of 16, and that doesn't sound very nice. So instead, I'm going to teach you a neat little shortcut. And this shortcut is going to save you tons of time. Let's remember the binary numbering system. You should all be familiar with powers of 2. Powers of 2 are something that are going to be essential to you. Well, this is exactly where it's going to come into play. So we can use powers of 2 to convert a number from decimal to binary. What if I told you that there's a really neat way to convert it from binary to hexadecimal? Well, there is. Let's go back up to our number line where we listed out the binary and decimal formats. And let's start listing out the hexadecimal values right next to it. So if we were to list out the hex values, we'll find out that these are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Well, remember, a binary numbering system is base 2. A hex numbering system is base 16. Now there's something special about the relationship of 2 and 16. Well, it turns out that 16 is 2 to the power of 4. So maybe that 4 can help us out. In fact, if we look at this, the largest hex digit can fully be satisfied exactly by 4 binary digits. Maybe you're onto something. Let's come up with a random binary number really quick. So our random binary number is 110, 111, 10110. Okay. So our random binary digit has how many digits in it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our random binary number has 11 digits. Let's try breaking this number into groups of 4, starting from the very right. So let's imagine that we break apart this longer binary number into smaller chunks of 4. So we know that 0110, which is the first rightmost chunk, is equal to hexadecimal 6. So let's write down a 6. We know that 111 is hexadecimal F. So let's write down an F. And 110 is, again, hexadecimal 6. We'd predict that this number is equal to 6F6. And you'd be correct. Go ahead, give it a shot. Try converting both the binary 1101111 number all the way to a decimal, and also try converting 6F6 to decimal. You'll find that it's going to be an exact match. That's because every group of 4 binary numbers can be assembled together to make one hexadecimal number. We can work out the math to exactly figure out why, but I'm going to leave that as, for now, I'm going to just leave this as a fun fact for you to have. So now what about converting from hexadecimal to binary? Well, let's say we have the hexadecimal number 15. Not decimal 15, but hexadecimal 15. Well, we know exactly how many binary digits this will require at maximum. At maximum, we will require 8 binary digits. That's because for every 1 hexadecimal digit, you need up to 4 binary digits, as we represented here. For example, the biggest hexadecimal digit is an F, and that needs exactly 4. Smaller ones may need less, and of course, any empty spaces we can just fill up with zeros. But the most you'll ever need is exactly 4. So let's try and break up 15 into binary. So let's first make out all the slots that we're going to need. 1, 2, 3, 4. 1, 2, 3, 4. And I personally like to have a small line down the middle to help me signify where the 2 digits stop. And then I can go ahead and start filling this out. So 5 in binary is going to end up being 101. So let's go ahead and fill that out. So that is starting from the right, 1, 0, 1. And of course, any empty spaces we're going to fill out with a 0. So now what about 1? Well, 1 is going to be just the binary 1 digit. So we're going to start off from the right, fill out a 1, and all zeros for the rest. So now we're going to make a prediction. Our prediction is that hexadecimal 15 is equal to binary 10101. And go ahead, I'd like you to test that out. Try converting 15 in hexadecimal to decimal and 10101 to decimal from binary as well. And you'll find that those two end up being exactly the same values. And the reason this happens is somehow related to 16 being 2 to the power of 4. Now, I don't want to go into too much detail of exactly how the math works out. If some of you are interested, feel free to ask and I'll go ahead and reply in a written response. But with this, you should be able to go from binary to decimal, decimal back to binary, hexadecimal to decimal, and while you can't go directly from decimal to hexadecimal, you can always go from decimal to binary to hexadecimal. So hopefully that's enough information to get you to understand exactly what the base 10 numbering system or the decimal numbering system is, the base 2 numbering system or the binary numbering system is, and what the hexadecimal or the base 16 numbering system is. Now, before I leave you off to do this week's exercises, I want to give you a little bit of a prior as to why do we care about this sort of stuff. Well, it turns out, in the end, computers are made of just ones and zeros. So these binary numbering systems are actually going to help us understand exactly how a computer works in the upcoming lesson. This is going to greatly ease your process of both debugging and understanding of the computer. So I look forward to seeing you next time, and hopefully you have as much fun with these numbers as I do. Adios.